Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. I welcome you all in class of Elementary Number Theory by David M. Burton. My name is Azmat Ali. In last lecture we discussed first 5 questions from problem 2.3. In today's lecture we will discuss the next 5 questions, question number 6 to question number 10. Among these 5 questions, some questions are very important and interesting. I will share the solution of these questions by using different techniques, by using alternative methods. So, inshallah, you will enjoy from this lecture. So, let us start from question number 6. In question number 6, for any arbitrary integer a, we have to verify the following: 2 divides the product a into a plus 1. 3 divides the product a into a plus 1 into a plus 2. In the first part, actually, we have to shown that 2 divides the product of product of two consecutive integer. If a is the first integer and then a plus 1 will be the second integer. So this is the product of two consecutive integers. And it also shows that the product of two consecutive integer is always an even integer. That's why it is divisible by 2. So let us verify this divisibility. By division algorithm, when we divide an integer a by 2, then we have unique integers q and r such that we can write a is equal to 2q plus r. This is the definition of division algorithm, where your remainder r lies between 0 and 2. If remainder r is 0, then your a is equal to 2q. Substitute this value of a is equal to 2q in this product, a into a plus 1, we have 2q into 2q plus 1, which is clearly an even integer, or it is divisible by 2, because this is the product, the product of two integer. One is 2q, that is even, and another is 2q plus 1, that is odd. So the final product is an even integer, so clearly it is divisible by 2. Next, when your remainder r is 1, then your a has the form a is equal to 2q plus 1. Substituting this value of a is equal to 2q plus 1, again in this product, we have 2q plus 1 and 2q plus 2. By taking 2 as a common factor from this bracket, we have 2 into 2q plus 1 into q plus 1. Again, this is a multiple of 2, that is an even integer, which is clearly divisible by 2. So in both cases, you can see that the 2 divides this product. In the next question, next part, we have to show that 3 divides the product of these 3 consecutive integers. Again, by using division algorithm, we can write a is equal to 3q plus r, where your remainder r lies between 0 and 3. So when r is equal to 0, your a is equal to 3q. Substituting this value of a is equal to 3q in this product, we have 3q into 3q plus 1 into 3q plus 2. Clearly this is multiple of 3, so this product is divisible by 3. When your remainder r is 1, then your a is 3q plus 1. So substituting this value of a is equal to 3q plus 1 in this product, we have 3q plus 1, 3q plus 2, 3q plus 3. By taking 3 as a common factor from this bracket, we have 3 into 3q plus 1, 3q plus 2, q plus 1, which shows that 3 divides this product, and hence 3 divides the product of these 3 consecutive integers. Lastly, when r is equal to 2, now your a is 3q plus 2. Substituting this value of a is equal to 3q plus 2 again in this product, we have 3q plus 2, 3q plus 3, 3q plus 4. Taking 3 as a common factor from this bracket, we have 3 into 3q plus 2, q plus 1, 3q plus 4, and which shows that 3 divides this product, and hence 3 divides the product of the 3 consecutive integers. Next, in the B part, we have to show 3 divides the product a into 2a square plus 7. You can do this question by yourself. This is similar similarly as the last part. In the C part, we have to show if a is an odd integer, then 32 divides this product, a square plus 3 into a square plus 7. As it is given that a is an odd integer, so I am letting a is equal to 2 and plus 1. So substituting this value of a in the given product, we have 2, by substituting a is equal to 2n plus 1, we have 2n plus 1 square plus 3, 2n plus 1 square plus 7. Expanding the square, we have 4n square plus 1 plus 4n plus 3, 4n square plus 1, 4n plus 7. This becomes 4n square plus 4, and this becomes 4n square plus 4n plus 8. By taking 4 as a common factor from these two terms, we have n square plus n. And again, when we take common 4 from these two terms also, the product is 16 into n square plus n plus 1, n square plus n plus 2. As n is an integer, so n square is also an integer. Let n square plus n is also another integer m. So replacing this sum n square plus n is equal to m, we have 16 into m plus 1 into m plus 2. As m plus 1 and m plus 2 are the consecutive integers, and the product of two consecutive integer by part A is always an even integer. So let this product m plus 1 into m plus 2, this is equal to 2s. So this become a square plus 3 into a square plus 7 equal to 32s, and that shows 32 divides a square plus 3, a square plus 7. Next, question number 7, this is also important question. We have to show that if a and b are both odd integers, then we have to show 16 divides a raised to power 4 plus b raised to power 4 minus 2. I will discuss this question by two different methods. As a and b are the two odd integers, so let a is equal to 2n plus 1 and b is equal to 2k plus 1, where n and k are some integers. Now substituting these values of a and b in the given expression, that is a4 plus b4 minus 2, we have 2n plus 1 whole power 4 plus 2k plus 1 whole power 4 minus 2. Also here will be minus 2 here. After some manipulation, we can have the following expression: 16 into n raised to power 4 plus k raised to power 4 plus 32 into n cube plus k cube, 24 into n square plus k square plus 8 into n plus k. Now I am discussing here the two cases for star. If n and k both are the even or odd, either n and k both are even or both are odd, in this case the terms n raised to power 4 plus k raised to power 4, n cube plus k cube, n square plus k square and n plus k are all even, and hence star is divisible by 16. You can notice that if you substitute any value of n and k, either both are even or both are odd. Suppose my n is 5, suppose my n is 2 and k is 4. Then you can notice that n plus k, this is equal to 6, which is an even integer. N square plus k square, which is equal to 4 plus 16, which is also an even integer. Similarly, you can check n cube plus k cube, n raised to power 4 plus k raised to power 4. All of these terms are even integers. Similarly, if you take n is equal to 1 and k is equal to suppose 5, then n plus k, this is equal to 6, which is an even integers. N square plus k square, which is equal to 1 plus 5 square is 25, which is equal to 26, again is an even integer. So in either both cases, if n and k both are even or both are odd, this complete sum is an even integer, and hence it is divisible by 16. There is no doubt that the first two terms are clearly divisible by 16. So the possibility is for the last two terms. But when n square and n square plus k square, this is an even integer. Suppose this is equal to 2s. This becomes 48s, and 48s, this is clearly divisible by 16. Similarly, if n plus k is an even integer, suppose this is 2s, this becomes 8 into 2s, which is equal to 16s. So it is also divisible by 16. So each of the term is divisible by 16, hence its sum is also divisible by 16. Case number 2. If one of them is even and other is odd, let n is even and k is odd. So let n is equal to 2r and k is equal to 2s plus 1. It is clear that the factors 16 into n raised to power 4 plus k raised to power 4 and 32 into n cube plus k cube, these are divisible by 16 because these are multiple of 16. These are divisible by 16. This is also divisible by 16. We check the possibility for the factor 24 into n square plus k square and 8 into n plus k. So consider the sum 24 into n square plus 8 into n plus k. Substituting the values of n and k, as we have supposed that n is even, so plug in n is equal to 2r and k is equal to 2s plus 1. So we have 2r square, this is 4r square, 4s square plus 1 plus 4s, and this is 2r plus 2s plus 1, which is equal to next we multiply 24 and 8, and after expanding these brackets we have 96r square plus 96s square plus 24 plus 96s plus 16r plus 16s plus 8. 96s square, 96s and 16s. These two terms have the sum 112s, and the remaining terms are same. Next 24 plus 8, this is also is equal to 32. By taking 16 as a common factor, we have 6r square plus 6s square plus 7s plus r plus 2. This shows that 16 divides this complete sum, and hence 16 divides star. What was the star? Star is actually the sum of these four terms. This star is this sum of these four terms, in which the sum of the first two terms is clearly divisible by 16, and the rest two terms is also divisible by 16. Hence, the sum of these four terms is clearly divisible by 16. So this is the first method, in which we have shown that 16 divides a raised to power 4 plus b raised to power 4 minus 2. Now I am sharing the second method. This is a very easy method, but in this method we are using some previous result. By using previous result, if n is an odd integer, then 16 always divide n raised to power 4 minus 1. This result we have discussed in mathematical induction. 16 divide always n raised to power 4 minus 1. As here a and b are also odd integers, so by using this result we can write 16 divide a raised to power 4 minus 1 and 16 divide b raised to power 4 minus 1. We know the result. If a divides b and a divides c, then a must divide their sum b plus c. So if 16 divides a raised to power 4 minus 1 and 16 divides b raised to power 4 minus 1, then it must be that 16 divide their sum. So 16 divide a raised to power 4 minus 1 plus b raised to power 4 minus 1, and which is equal to a raised to power 4 plus b raised to power 4 minus 2. So this is a very simple and easy method that you can use. Question number 8. This is also very interesting and important question. Prove the following. The sum of the squares of two odd integers cannot be a perfect square. You can check this question, this statement, by taking any particular examples. The sum of squares of two odd integers. Suppose my first integer is 1 and my second integer is suppose 5. Now if you take sum of square, this becomes 1 plus 25, which is equal to 26. And you can check that 26 is not a perfect square. So in this question we have to show the sum of squares of two odd integers cannot be a perfect square. Let a and b are odd integers, and we suppose that their sum of square is equal to a perfect square c square. Since a and b are odd integers, this implies a square plus b square is an even integers. If a is odd, then a square will be an even integer. It will be, an odd integers. Similarly, when b is odd, then b square is also an odd integers. And their sum a square plus b square is equal to odd integer plus odd integer, and the sum of two odd integer is always an even integer. So it means if a square plus b square is equal to c square, it means c square is an even integers. Next we have a result. We know that an even integer which is also a perfect square leaves the remainder 0. You know, all the integers which are perfect square, when we divide them by 4, it always leaves the remainder 0 or 1. For example, consider 36. 36 is a perfect square, that is 6 square. When you divide 36 by 4, the remainder is 0. The next, suppose 49. 49 is also a perfect square. When you divide 49 by 4, it leaves the remainder 1. So when you divide any number that is a perfect square by 4, it leaves always remainder 0 or 1. But here are the two categories. It is possible that your number that is a perfect square is even, or it may be odd number. But if your number is even and also it is a perfect square, then if you divide that number by 4, it always leaves the remainder 0. In other words, we can say that a perfect number that is an even, that is also even, it is a multiple of 4. So it means c square should be of the form 4k, because if c square represent a perfect square, so it should be a multiple of 4. Multiple of 4 means it can be written as in the form c square is equal to 4k. Now we suppose the given conditions that a and b are the odd integers. Suppose a is equal to 2n plus 1 and b is equal to 2n plus 1. Now I calculate a square plus b square, which is equal to c square. So substituting the value of a here, we have 2n plus 1 whole square and b is equal to 2n plus 1 whole square. And after expanding and taking 4 common, we have 4 into n square plus n plus m square plus m, and this 1 plus 1 is equal to 2. As n and m are the integers, so their square and their sum is also an integer. So let's suppose this is equal to some integer t. This is equal to 4t plus 2. This shows that your c square is equal to 4t plus 2 form. This is not equal to exact 4k plus 4k form. Hence a square plus b square, this is not equal to, these two have the two different forms. So a square plus b square can never be equal to a perfect square c square. Hence sum of square of an odd integer can never be a perfect square. Question number 8b, this is also interesting and important question. Show that the product of 4 consecutive integer is 1 less than a perfect square. For example, consider the product of first 4 consecutive integers, like suppose first 4 positive consecutive integer, 1 into 2 into 3 into 4. The product is 24, and 24 can be written as 25 minus 1, which is equal to 5 square minus 1. And what does this show? This shows that 24, that is the product of the first 4 consecutive integer, is 1 less than the perfect square, that is 5 square minus 1. Similarly, if you consider the next product of next 4 consecutive integer, 2 into 3 into 4 into 5, this is equal to 5 4 the 20, 23 is a 120, 23 is a 60, 62 the 120. This is 120, and 120 can be written as 121 minus 1, and 121 is actually the square of 11 minus 1. This shows that again you can notice that now again the product of 4 consecutive integer is 1 less than the perfect square, that is 11 square. So I am sharing the solution by a very simple and just by using the algebraic method. Let the first integer is a, then the product of 4 consecutive integer is given by a into a plus 1, a plus 2, a plus 3. Just by after multiplication of these 4 factors, we have a raised to the power 4 plus 6a cube plus 11a square plus 6a. By adding and subtracting 1, we have this polynomial in a, and if you take the square root of this polynomial, we can get a square plus 3a plus 1. In other words, these 5 terms can be enclosed in the square of these 3 terms, sum of these 3 terms. And if we suppose this is equal to c square, c square is any integer, so which is our required form, that shows that the product of the 4 consecutive integers is 1 less than the perfect square. Now an alternative way of calculation is, this is my product of first 4 consecutive integers. Let us pair a with a plus 3 and a plus 1 into a plus 3 as. Multiply a into a plus 3, we have a square plus 3a, and multiply these two factors, we have a square plus 3a plus 2. Let this sum a square plus 3 is equal to some integer n. This becomes n into n plus 2. This product becomes n into n plus 2, and this becomes n square plus 2n. By adding and subtracting 1, we have n square plus 2n plus 1 plus 1. This is equal to n plus 1 whole square minus 1. Again, you can see that this is the 1 less than a perfect square. Next, question number 9. This is also an interesting question. Question number 9. Establish that the difference of 2 consecutive cubes is never divisible by 2. For example, suppose the first integer was 1, whose cube is equal to 1, and the next integer is 2, whose cube is 8. Now the difference of these two consecutive cube is equal to 7, and you can check that 7 is not divisible by 2 because this is not an even integer. Similarly, if you choose the next 2 consecutive cubes, for example, next is 3 cube, which is equal to 27. If you subtract 8 from 27, 27 minus 8, this is equal to 19, and 19 is again an odd integer which is not divisible by 2. So now we prove this question in general. Let n be an integer, then the difference of 2 consecutive cubes is given by, if first integer is n, then its cube is n is, suppose n is my first integer, then its cube is n cube. The next consecutive integer is n plus 1, so this difference represents the difference of 2 consecutive cubes. Now I have 2 cases here. If n is even, then n cube is also even, because any power of an even integer is always even. Any power of any integral power of an even integer is always an even integer. Any positive integral power of an even integer is always an even integer. So n cube is an even integer. But if n is even, then n plus 1 is odd. N plus 1 is odd, and cube of an odd integer is always odd. This shows that this is the difference of odd minus even integer. This is my odd integer and this is my even integer, and the difference of odd and even integer is again an odd integer, and this is not possible that odd integer is divisible by 2. So in this case, we can check that the difference of 2 consecutive cubes is not divisible by 2. If my n is odd, then n cube is odd, but in this case n plus 1 cube will be even, because when n is odd, then n plus 1 is an even integer, and any power of an even integer is an even integer. So this becomes even minus odd. The difference of even minus odd integer is always an odd integer. Again, an odd integer cannot be divisible by 2, so in both cases the expression is not divisible by 2. The second method is considering the difference n plus 1 whole cube minus n cube, and after expanding the cubes and after some algebraic calculation, we can get this expression 3n into n plus 1 plus 1. For all integer, either these are odd or even, this number 3n into n plus 1 plus 1, this is always an odd integer. An odd integer is never divisible by 2. Next, question number 10. This is the basic question related to greatest common divisor. For a non-zero integer a, we have to show that the GCD of a non-zero integer a with 0 is always equal to absolute value of a. GCD of the same number is equal to a absolute. The GCD of a with 1 is equal to 1. So start from the first part. GCD of a and 0 is equal to a absolute. Any non-zero integer is divisible by 0, is a divisor of 0, sorry. Uh, you know that every non-zero integer divides 0, that is, if a is any non-zero integer, then a must divide 0. It means a is the divisor of 0. Further, plus minus a are the common divisor of a and 0 both. Because if a divides 0, then minus a also divides 0. It means there are the two common divisor of a and 0, which are plus minus 1. Lastly, uh, for any non-zero divisor C that divides a must be less than or equal to a. This is the actually definition of common divisor. And C is less than or equal to a absolute. In the definition of common divisor, we say that if a and b are the two integers, nor both of them are 0 at the same time, suppose the GCD of a and b is equal to d, then d is called the GCD of ab if d divides a, d divides b. This is the first condition. Second condition says that if C is any other common divisor of a and b, and then C divides D, and this implies C should be less than or equal to D. This shows that D is the greatest common divisor of A and B. So if C is any other common divisor of A and B, then C must divide A, and it should always be less than or equal to this GCD. So C less than or equal to A absolute. This shows that A absolute is the greatest common divisor of A and 0. Hence, the GCD of A0 is equal to A absolute. In the second part, we have to show GCD of integer A is equal to A absolute. As plus minus A divides A, this implies A absolute divides A. This shows A absolute is the common divisor of A and A. Let C be an other common divisor of A, then C divides A, and C is less than or equal to A. This implies its absolute value is always less than or equal to A absolute. This shows that A absolute is the greatest common divisor. GCD of A and 1 is equal to 1. As 1 always divides any integer, so 1 divides A. Also 1 divides itself. This implies 1 is a common divisor of these two integers A and 1. Let C be an other common divisor of A and 1 such that C divides 1. 1 means the GCD. C divides 1. This implies if C divides 1, it will always less than or equal to 1. This implies its absolute value is always less than or equal to 1. Hence, 1 is a GCD of A and 1. And this completes our lecture. So, I hope now you have a clear understanding of these interesting questions. If you have any question, you can message me. Inshallah, I will reply you. See you in the next lecture. Inshallah, in the next lecture, we will start from question number 11. So, take care. Allah Hafiz.